Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, happy to have Yuri Lifshitz giving a talk today, currently a postdoc at Caltech.
Yep, thank you. Nice to be here. So let's start with general field just for 1 second. So the general field is web algorithms. So it's a collection of many many problems to solve in real life. And my focus for last years in research was trying to do some theory useful for this. And I was looking for the most repeating algorithmic problem in this field. So I was trying to figure out what is like the bottleneck or what is the interesting place where theory can contribute mostly. So before coming to this, there are I see 3 ways to measure the performance of algorithm. So it's like computational resources, time and space. There is like machine learning approach when we focus not on speed but on quality of prediction and agreement with labeled training collection. And with web algorithms, there is some difference, which is the 3rd way to evaluate algorithms, which is like user satisfaction or revenue in advertisement systems or like click-through rate. So for click-through rate, you cannot actually generate the labeled. No, you can generate some labeled data, but it's always not enough. So sometimes you really need to test some algorithms on real users. And this is an advantage to work here at Microsoft, because here you probably can test on real users, while here at Caltech I cannot test. So during my academic time, I was focusing, unfortunately, only on the first part. Sometimes it's not the bottleneck. Sometimes it is. So, okay, and looking for all these web algorithms, I identified the problem which seems to be like the most repeating one, which is nearest neighbor search or similarity search. And this is the problem of searching within some data set, and data set and the underlying space has some similarity function. Sometimes a metric, sometimes not a metric, so it does not have triangle inequality. So, but the question is, it's not a single algorithm, it's like 2 algorithms. So to pre-compute data, to organize them into some data structure, and then the second algorithm, given a query, quickly identify the point in the data set that is most similar one, so it has the highest similarity value or the smallest distance value to the query point. So this is like mathematical description of the problem. And so just an example with pictures. So just the same problem, similarity search. So given a lot of pictures, you need to pre-compute them and to store them in some data structure in such a way that given a new picture, you need to find the one which is the most similar one. You probably can't do this. So I'm coming from California, so this is Californian example. And okay, that's the problem. But I was looking for this problem in the web context, so not for images. So the quick overview of contribution is a new approach. So I would say this is a new assumption. Essentially, this is a new assumption. So in general, the problem of similarity search for any similarity function for any data set is intractable. So you cannot suggest a single algorithm for all the data sets, all the similarity functions, because that in general case, you need to check every data point with the query point. So you need either assume something about the data set or about the similarity function or about both. So essentially, I contribute with a new form of assumption. And this new form of assumption leads to new algorithms. For nearest neighbors, for near duplicates, it is a similar problem. It's not preprocessing plus query. It's just offline problem. You given a data set to identify all pairs of similar objects. And also another problem we'll probably discuss later related to small worlds. And there are some other work with the nearest neighbors I have done, in particular website. So I set up a website trying to collect in a single place all efforts, all what other people do about nearest neighbors. So I have tutorial with 4 lectures and slides and videos, and I have bibliography like 100 or 2 references, and so surprisingly, a lot of people work on this. So it's, I think, incomplete list of people who contribute to nearest neighbors. So you can see quite a lot of people. So please suggest more people. I obviously it's not complete. Okay, so the outline for today's talk is first I would like to discuss why the previous theory not always work well for web. Then I introduce my new assumption. Then we discuss algorithms, and hopefully I will have time to show you one technical trick, and then some directions for further research. Okay, theory and web, both in context of similarity search. So I tried just to look what kind of application similarity search has in web, what kind of similarity search algorithms we have in theory, and look whether they match each other or what are the mismatching points, mismatching assumptions, and then come up with new approach. But this is not the full picture, so there should be number 5, which is like testing new algorithms on real life. And this is like just starting now. So we have one implementation, a couple of tests, but not really a serious work. So a serious work is ahead of us. Okay, so applications. So all kind of recommendations and ad targeting and all kind of search can be just stated that they're part of similarity search, because in any case you have some relevance of movie to the person or of advertisement to a website to put in, or a news article to my profile of interests. And then given all news articles, we need to identify one quickly when I log into the website with personalized news, like Find Dory, to find the most relevant news for myself and show me them. Or with ad targeting, the same thing. So given a website and knowing that some user coming to it, we need to go to our ad data set and identify the context ad that it's most similar to the given user and given publisher. Okay. So now theories. So that's not just a single algorithm. So there are quite a lot of them. And so like they're starting like 50 years ago and publishing every year new algorithms. So when you're trying to choose one algorithm for this problem like ad targeting, you're a little bit lost, right? So you don't know which one to choose. So what you do? So basically I suggest instead of looking at this picture, looking at this picture. So my personal choice of 4 main ideas in the 50 years history of nearest neighbors. So first one is branch and bound. So you're trying to build something like a tree out of all objects in the data set. And there is some information, some clever information in the internal nodes. And you compare your query with this clever information in the internal node. And sometimes you have to go to both branches. But sometimes this clever information that basically say what is the difference between left branch and right branch, it suggests that one branch you can skip because it's too far away from query. And then you like cut some branches and visit only relevant ones. And hopefully you will visit much less than the entire tree. Hopefully. So the second idea is like greedy walk, or like improvement algorithm, or hill climbing it's called sometimes, or local search. So you start from some object. So you start from some advertisement for this given website, and then looking for a similar advertisement. If there is one more relevant, you move there. Then you look around. If there is something more relevant, you look go there, and so on. So you're moving in the space of current objects, trying to moving every time closer and closer until you finally reach the most relevant one. The third idea is all kind of mapping or hashing, projecting. So instead of living in initial space, you're trying to go to the beta space, probably low dimension or beta structured, or instead of the space without structure to, I don't know, coordinates. And then in that space, you perform the search by some of other methods. And hopefully this mapping will not destroy the structure of initial data sets. So the things that were closed in initial space are closed in a new space, other way around. Okay, and the last idea, which appears like last decade, was epsilon nets. So it's like to building a map of the data set. It's like geographic map. So there are countries, there are states in the United States, there are counties, and then there are cities, and so on. So you are trying to have a map on all scale. So the big groups of objects, then the smaller groups, and then the very small groups, and so on. And so when you search, you're first trying to identify the relevant big groups. Then within these big groups, you're trying to identify relevant smaller groups, and so on. This is the intuition. OK, so why not use one of these? So the differences. The first difference is that the nature of similarity function in the web sometimes is very messy. So in some theoretical models like Euclidean model, so it's the two vectors of coordinates and Euclidean distance, very clean. And that they assume that all coordinates have like the same nature, so they are numbers, for example. But sometimes it is like more like a graph. Or sometimes it has time, it has location, it has predefined dictionaries. It has so it's got graph, predefined dictionaries, integers, real values, and coordinates, and they all you need all to combine all this to get the final similarity function or relevance function. Yeah, I think you're familiar with web search. So with web search, when you have a query phrase and when you have website, you combine a lot of factors to compute the score. Like in particular, if it is a personalized search, you look what was your previous searches, so you personalize that somewhere. So this is a particular example for recommending research papers to people. So you can say that you can recommend something that's cited by my friends, or something that has intersection by keywords, or something that is co-cited with something I like. Presumably, I like my own papers, and so on. So in this graph picture, so the similarity is high when there is a lot of chains of different factors that link from scientist to paper, and when these chains are short and the weights are heavy, like, I don't know, I'm the single author of this paper. Or paper is co-cited with that paper by many people, then it is heavy. OK, so another probably bigger problem with implementing theory directly is the triangle inequality thing. So when we speak about distance, we assume triangle inequality. And many algorithms, like all branch and bound algorithms, they assume triangle inequality. Because what they do, they use the following logic. So they use the logic that if this is a query and I test it against P, and it turns out to be really far away, and I know that P prime is close to P, then I need not to check P prime, because by triangle inequality, this should be ln as well. So that cannot be a nearest neighbor. This is the logic of branch and bound. But I will argue later that it is broken in some web data sets. And the second assumption, more technical and appeared last years, is doubling dimension assumption. This is the assumption, something like that you look for any ball in the data set, so some points coming to the ball. So ball is like all points that are within some distance from some center. And you ask how many balls of twice smaller radius, so this is like radius to r, how many balls of radius r you need to cover the same subset. And if this number is limited, then the doubling constant is small. OK, so the doubling constant is just the maximum over all these particular big balls, maximum number of balls you need to cover it. And the algorithms based on doubling dimension, they work well, means work fast, when this doubling dimension is somewhat, this doubling constant is somewhat around log n. There is a problem with these assumptions. They simply do not hold for many data sets. And the problem is that with data set, so for images, they hold. So if you, my example with images, like with Arnie and the other guys, it was okay. So we assume that really when there's the same person, if we have the right features, it really looks different Arnie to Arnie would look really similar and other looks really different. But with, say, with texts, just with text, not websites, if you look for, say, news articles, and you take any 2 news articles from CNN, then the typically intersection by keywords is less than half. Or if you take a social network like Facebook or Spaces, then if you take the 2 people and look for intersection of their friends, that would be less than 50%. So I have 100 friends, Misha has 100 friends, intersection is 20 friends. So our similarity is like 20 friends, but our distance, our dissimilarity, is like 80%. So we are far from each other. And Misha still can be the person who has the largest number of joint friends with me, this 20. Others have less than 20. So when we have for almost all or for all pairs these distances, say, between maximal possible value and half of maximal possible value, this logic doesn't work. Whatever distance here is it is, it is at least 1/2, right? And here it is at most 1. So, okay, you know that this would be at least 1/2, but you know that for any point here, the nearest neighbor also has at least 1/2. So you cannot prune any particular object by branch and bound in this case. And also doubling dimension is, doubling constant is n, is not log n, because if you take a point and take the distance 1, so it's like probably 0 number of joint friends with me. I have 100, 0 number of joint friends means distance 1, distance 100 if you like. But if I take the 50% radius, like twice smaller, like having 50 friends out of 100, there is just me, myself. Nobody have 50 friends joined with me. So that means ball twice smaller has just 1 point. Ball twice larger has all points. So you need so many balls twice smaller radius to cover the thing. So that means that directly for this kind of data sets where we have this kind of separation effect and we have a messy similarity function, not as clean as Euclidean distance as a formula, and it can change, right? You can re-evaluate factors. Then the old methods have some troubles. Well, so we need to do something with this, right? So, and now we can come to new approach. So first thing new approach is doing is instead of restricting, so instead of adding some additional assumption, is doing opposite thing. I'm going to make my problem even more complicated. It's a kind of strange. So previous interview, I got a question about it. OK, so instead of thinking I have similarity values, I would say I have only comparative information, much smaller information. So instead of knowing what is my similarity to Misha or what is my similarity to Dennis, I know just that Misha is the most similar person here in this room to me. And Anton is the second most similar, and Dennis is the third most similar, and so on. So I just know the ordering of all of you with respect to me, how similar you are with respect to me. So I have this ordered list. So this is myself, and this is Misha, Anton, Dennis, and so on. So we have this list. And so I don't have the formula. I don't have coordinates for any of you. But I can ask the questions like, this is myself, and I ask about Misha and Anton. Who is more similar to me, Misha or Anton? And Oracle will give me an answer, say, Misha is more similar. So I assume for today there is no ties. So everyone is, there's strict order. So what kind of, just simple, stupid question. How many different questions can I ask to such an Oracle? I assume I have n people in the room. Huh? Yeah, number of triples, but for every triple I have like 3 questions, not 1. Because I can say for triple with respect to me, with respect to you, and with respect to Anton. But something like n cube, so this order. So instead of having, I don't know, infinite information about exact values of similarity, I have just a kind of n cube of bits. This is all my description of the data set. It's pretty limited. But at the same time, it's very general, so it can work for any similarity space It does have no restriction on any nature of similarity, so it's pretty general. Before introducing now the assumptions, so right now I was just making problem more complicated. Now I need to make it easier back. So I need to make an assumption. Before making an assumption, I need the notation. So the notation is the rank function, and it is our new friend instead of distance. Our new best, most used word in all this approach. So this is rank function, and essentially it's just the position of the object in this sorted list. So the rank of Dennis with respect to me is 3. He's third most similar person in the room. And rank of myself with respect to myself is 0. So I'm on the 0 position to myself. So that's the notation. And now an assumption is a kind of triangle inequality for ranks, but a little bit relaxed with some constant. So I would say that the data set is good, and it would be easier to work with it if there is a nice, small constant such that for any triple, the third rank is limited by some constant times 2 other ranks. Just repeating it on whiteboard. So if I know that somebody is, I don't know, has rank 7 to me, so 7th best friend, and somebody else has 11th best friend to him, then this person is at most this major constant d times 7 plus 11. So I take the constant d such that this holds for all triples. This is like I'm working here as a theoretician, so practitioner would say that we need constant d such that for most of triples that's true. But to make the theoretical analysis of algorithms, I was forced to assume that this is true for all triples.
Could you say that d measures how much triangle inequality is broken in your case?
Sorry?
Does d measure how much triangle inequality is broken? Isn't it effectively sort of a measure of how far you are from achieving triangle inequality?
It's slightly different. I would say it's independent, because even if triangle inequality is true, say all distances are within 1/2 and 1, then triangle inequality is always true. But you can get any ordering.
Oh, it's the range, sorry.
Yeah, so it's for ranks, right? And it's about how different ordering are consistent with each other. So if we are good friends and we have 2 ordering, one for you with respect to you, another with respect for me. If we are good friends, I assume that this ordering are kind of similar. So if somebody has position 100 in your list, it has maybe position from 50 to, I don't know, 200 in my list, because we are, I don't know, best friends. Something like this. So there are many questions about this assumption. So, okay, just to repeat. So the combinatorial framework is assuming that we have only comparative information and assuming disorder inequality. And right now you have a lot of questions, I know. So probably you have one of these questions, probably some more. So let me try to answer one by one. So first of all, really, what about metric case? So assume we have triangle inequality. Does it imply disorder inequality or other way around? So the answer is no. They're kind of incomparable. So there might be metric space with bad disorder. There might be not metric space with good disorder, small disorder. And disorder is a parameter of data set. It's not a parameter of space. So it does not matter how dimensional is the space where these points are. It's only characterize what is the respective ordering. If this respective ordering with respect to any particular point is like consistent with each other, or it's like totally random. If it's totally random, then it's a bad data set, no matter in what space it lies. Okay, now the second question is, okay, you assume that disorder is small. So what I mean by assuming that disorder is small, I will later on analyze time of algorithm in terms of d. So I will say that, say, nearest neighbor goes in time d log n. So if d is like n, that is really bad. It's like checking every one. But if d is like square root of n or log n, then it's a kind of improvement. So assuming that, hoping that d is small. So when it is small. So one answer is when we have a so-called intrinsic dimension phenomenon. So assuming we are living in a large dimensional space, but all points are lying along with some small dimensional manifold. So there are like billions of features, so billion dimensional, I don't know, space of all possible text, so all possible websites, all something else. But websites are quite similar to each other, and so they are lying along the curve or along the probably two-dimensional manifold or something like this. And then hopefully the nearest neighbor problem is easy, or it is as easy as it the easiness of the problem is proportional to real dimension of the data. So instead of being, say, there is no polynomial algorithm in dimension in general, so it is usually exponential. So, but instead of having exponent in dimension of the feature space, we would like to find at least algorithm that it is exponential is just in intrinsic dimension. That's what we can hope for. And yes, there is one particular example. So now I would like to argue that the disorder of the data set is, okay, it's a kind of function of the intrinsic dimension, and there is a more or less clear correspondence between the, say, assuming Euclidean case, so between dimension and disorder inequality, disorder constant. So assuming I have 3 points in some Euclidean space, say k-dimensional, and here I have distance r, and here I have distance q. So, and assuming I have uniformly distributed data set, then what is the rank of this point with respect to this point? It's proportional to r to the k, right? Because this point, what rank of it? It is like the number of points that are within this circle, that are closer to this point than this particular point. And the number of points, if we have a uniformly distributed data set, it's proportional to the volume. The volume has dependence on the real dimension, so it's proportional to r to the k. And the second rank is proportional to q to the k. And the third rank is proportional to this distance to the power of k. So it is at most r plus q. Here I use usual triangle inequality to the power of k. So if we would like to write something like disorder inequality, we will get something like that. The third rank is no more than, okay, the third rank is no more than r plus q to the k, which is no more, and this is like a simple calculus fact, 2 to the k minus 1 r to the k plus q to the k, which is proportional to, with the same constant, to 2 other ranks. So we have here the constant that it is exponential. Okay, it's exponential, unfortunately, but exponentially it's like in real dimension. So if we have this small manifold, we have the same proportionality of these balls. So it's a kind of hand-waving proof, but still, that we will, in this manifold case, we will have the constant that it is exponential in intrinsic dimension, but not in big space dimension. So experimental values. So far there were 2 experiments. One was with Reuters texts and cosine similarity measure. And another one was some biological data sets like genomes. So the first one was by my co-authors, and the second one was by independent person from Broad Institute of Biology at Harvard MIT. And so both cases were exactly very similar results. So in average, D is very small. So just reminding you what is the disorder inequality. So in general, the third rank is like 2, 3, 4 times more than sum of 2 other ranks. But there are exceptions. There are exceptions when it is 100 times or 1,000 times more. But these exceptions are relatively rare. So most of cases, it is holds. So that gives us the hope that theoretically proven algorithms in this idealistic model can still work in real data, but we need, of course, to check it later. Okay, more questions. So now we need to also to compare with other concepts of intrinsic dimension. I will do it a little bit later because I need to introduce some more terminology. Maybe some questions here, because I just introduced the most new concept in the talk. So maybe, yeah.
So what were similarity measures that you guys used in the experiment?
So as I said, for Reuters collection, it was like cosine similarity measure. So it's like you represent texts of news articles as a vectors, TF, IDF vectors. And then you simply get a scalar product. The highest scalar product is the highest similarity. Basically, it's a form of number of joint words between two articles, just weighted by their inverse occurrence throughout the whole data set. Yeah?
So you're claiming that D is often going to be small. Now you haven't shown yet how we're going to use this, right, to speed up.
Yeah. It's the next part of the talk. Okay. Okay, so some advantages. So I will try to evangelize this concept a little bit before we go to algorithms. So it doesn't require usual triangle inequality. So the disorder can be small even in these bad cases when this 1/2-1 separation effect holds. And it's applicable to any model. We don't have any assumptions about similarity function, coordinates, whatever. And if we would like to, instead of assuming we don't have similarity function, so we're trying to figure out what is the right similarity function. Sometimes it is the case. Maybe most of the times it is the case. So, and then if we, for just making this nearest neighbors algorithm, we need not actually to learn what is the similarity function. We just need to learn what is how to order things by the similarity order. So instead of trying to figure out what is the right similarity function between me and Misha and finding out that it is probably exactly 0.134739. So what does it mean? It probably means nothing. Yeah? But this, to learn what is the right way to order people with respect to each other is probably sometimes more meaningful. And another thing is like local sensitivity of this stuff, because if you look for, I always scale to the, instead of using distance, I using the rank. So if you take that a person and his, I don't know, 100 neighbors in New York, you get just one building. And if you take it in LA suburb, then you take a district because everybody living in the house. So it's like automatically scales to where you live, whether you live on the dense subregion of the data or highly dense or desert or something like this. And sometimes it's useful. So the main thing there are two things to be done in nearest future is testing, implementing, and to understanding even in theory what can we guarantee if we have just average disorder assumption.
Well, yeah. But you mentioned before there's sort of a cubic aspect. For any one query, you may have to look at multiple pairs and n squared things you're looking at for each query. Whereas normally for linear scan, we only have to look at n things. Right? So there's an n squared versus n issue too, isn't there?
Where is an n square issue?
Well, so normally if you do nearest neighbor, all you got to do is cut out n.
Yes, yes.
Here you got to think of pairs of guys, like this relative aspect. So potentially you've got an n squared complexity.
If I would ask Oracle all these questions, yes, but surprisingly, there is a way to deal with this, and this is one of the main technical results. I will talk about this.
No, I think this way to do it. I'm just saying if you're going to set this up as a motivational thing,
Yeah.
the thing you have to handle.
You can avoid, yes. Actually, there was with co-authors I published 2 papers. On first of that, we have n square preprocessing because we needed all these sortings, like to get all ranks. And reviewers write, okay, the paper is good, but please deal with that. And luckily, with the second paper, we overcome it. Okay, now we need, once we have this new concept where we don't have triangle inequality, but we have relaxed triangle inequality for ranks, the first idea to do is just to download papers from the web, and then you do like Control-R, and then you replace all distances by ranks, compile the paper, and look whether it works or not. So that's approximately what we try to do. So in particular, when you look for the definition of the ball, instead of metric ball, you can think about combinatorial ball. So you just take a person and take the 10 best friends, and this is the ball of combinatorial radius 10, and so on. OK, so this is the first definition. Now you can define the combinatorial net. So in calculus analysis course, there is a thing called epsilon net, when you cover all the data set by epsilon radius balls that altogether cover everything, and none of them cover the center of any other. So there's a kind of separation. And you can do this. How to build, by the way, how to build such a net? What is the most natural way to build an epsilon net or combinatorial net? Just to get you involved. I mean, assume you need to get a collection of balls that altogether cover the data set. What's the easiest way to do it? Yeah, right. So you take a ball, remove all points from the data set, take an uncovered point, take a ball around it, remove the ball, and so on. That's what you do, and I don't assume anything better than this. OK, and so you can do the same with combinatorial things, but the rank is not symmetric. So the two problems, we have triangle inequality relaxed to a constant, and the rank is not symmetric. So the separation, I defining the combinatorial net, I a little bit relaxed the definition. I asked that the separation effect should hold just in one direction. So either one center to another one has rank more than 10, or in other direction, if the 10 is the radius of combinatorial net. By the way, there is a nice corollary of the definition. So the definition was about triple, but if you plug in a degenerate triple, when 2 points out of 3 are just coincide, then you get the property something like that rank xy is smaller than the rank yx. So in particular, we assume that reversing the rank, we can get at most d times more or less. So that means that when I speak about R net and I take any two centers, that in one direction they should be R separated, in another direction R divided by D separated. OK, so now I can say a little bit about comparison to two other concepts of intrinsic dimension. So first of it is expansion rate or growth rate, or sometimes called it's very related to a thing called Karge rule dimension. So basically, Karge rule dimension is just log of C. So it is assuming the following thing. It's assuming that you take a point in the data set, you take a number of points that are in the radius R, and then you look the number of points in the radius 2R, and look how much more you have. This is expansion rate. And unfortunately, if you take the people in my social network example, if you take people that have 50 friends with me, you have just me, and if you have OK, so it's like OK, so I have 100 friends, right? So here is the small ball would be something like having from 50 to 100 joint friends with me, and the second one would be from 50 to 0 friends with me. And in this ball, there is just 1 point, and in this ball, it's all points. So unfortunately, expansion grade, this old assumption, does not hold to some these social examples. With text, the same. If you take any particular text of news article, if you take a small ball, you take just this article, you take a little bit twice or 3 times larger ball, it takes all news articles. So the growth rate is not really limited. But in some other examples, it is limited, like in geography, driving directions and driving distances. We have 2-dimensional Earth, so Earth's surface. So more or less, when you double the distances, more or less double the, not double, but 4 times the square. OK, so this is one thing. And luckily, there is clear direction. So if some data set has limited expansion growth. It has limited disorder constant, just at most c squared. And this is 5 lines proof. And another thing is doubling dimension, and it is incomparable. So sometimes doubling is small and disorder is large, sometimes other way around. And this is, in context of nearest neighbors, it was introduced by a very influential paper by Krautgamer and Lee, like 4 years ago, or maybe even 5. And this is about the following thing. So it's about like having a ball of radius 2r. We not compare it with the population of ball of radius r here, but we ask how many balls of radius r we need to cover the whole big ball. And this is the doubling constant of the data set. And it turns out, yes, so sometimes this constant is small, disorder is large, or other way around. But again, I argue that this assumption does not apply to some web data sets. Again, with this separation effect. So if you take a ball with like up to 0 joint friends with me, you get everything. But if for every person you would like take the ball just twice smaller radius, so it's like having at least half joint friends with him, then you will, by these balls, you need a lot of balls to cover this. So the doubling constant will be large. OK. New algorithms. So assuming we have this disorder D, so there is one like auxiliary algorithm that underlies all the remaining algorithms. So by itself, it's just technical thing, but it's really reused everywhere. So it's an algorithm to compute combinatorial net. Not just a single net, but the family of nets. So it's like, first we take the ball of radius n that cover everything. So simply we take a point, we take n best friends, meaning all friends, all people in the system, and OK, this is one ball, it's cover everything. Then we try to identify several key people such that if around every person we draw a list of n half of all people, altogether we cover the data set. This is second layer. Then we go to the next layer. So we're doing it by just adding people. So the person who is on the first level will be repeated on the all levels down. So then we're trying to identify the sampling of several people such that we take the n divided by 4 around every of them, then altogether they cover the whole thing. And we would like to build this till the end, so log n levels. And surprisingly, and we need a lot of pointers. So we need pointers like for every point, we need pointers to all particular balls here that cover it. So it's like inverted index and direct index. So for every ball, we will store the list of points that are covered by that. And then we need some brother links or cousin links. It's something like for every ball, we will link to a close by. So it's like if we have like countries, counties, and states, and so on. So then for every state, we have like links to neighbor states, and for every county, we have links to neighbor counties, and so on. It's like knowing who is around on the same scale. So the first technical result, and the most technically difficult one, is to prove that combinatorial net can be constructed in this oracle model. So we just ask these questions about who is closer to whom in subquadratic time. So we need not to get out of the oracle the full orderings. Because if somebody is like in the second half, so it's one of the second half the least similar friends, we're actually not very interested which position he is.
Is time proportional to the number of oracle queries that you need to make, or is there any other computation?
Of course there is. There is. So I think the number of there should be some other polynomial here. So maybe something d to the 4n log square, and probably it's just one log. So maybe the number of oracle queries is something like n log n d to the 4 or something like this. It's a little bit smaller, yeah. I will tell later what is the most repeating procedure here. What is the main trick which will repeat really many times during algorithm, and it's not about Oracle. Okay, so this is the first technical result. And now nearest neighbor. So there is deterministic exact algorithm, which is quite strong claim. In this model, in this idealistic model, it assumes that disorder inequality holds for all triples. That has preprocessing time the same as combinatorial nets, and the search time is just d to the 4 log n. So it's pretty good. So if like in previous papers, it was theory papers. It was assumed that the doubling constant or growth rate is logarithmic. So if we assume the same for our disorder constant, then we have logarithmic, polylogarithmic search, which is really nice.
And again,
Yeah.
before log n, these are mostly Oracle queries.
Again, it might be smaller polynomial out of D. No, it isn't. No, it's really the same number of Oracle. Here it's the number of Oracle queries. Okay, so there are a couple of variations. So first of all, we have randomized algorithm that has even faster nearest neighbor search. So I cannot believe we can break this. This is like really the fastest we can do. It's like one dependence on D, one dependence on log n. Like both seems to be like unavoidable, because even in like in numbers on the line you need log n, and the D accounts for the like intrinsic dimensions. So there should be some factor like if intrinsic dimension is higher, then the complexity is higher. So it's like reasonable to have some D. And also we have like linear data structure. So we have still like this preprocessing time, but afterwards we can clean the data structure in a way that it has just linear size independent on D. So there is no D dependence, just really universal constant. But the search would be a little bit slower, like D to the 7 log n. So we'll just postpone more work to the search time. Just maybe sometimes this trade-off makes sense. Okay, so next thing is near duplicates, and here we have also like a result never seen before, because we have subquadratic algorithm, deterministic subquadratic algorithm. So we can promise to find all near duplicates. So we have some threshold, assuming our oracle can say whether we me and Misha are similar enough to be qualified as near duplicates or not. And so given this, we can find all pairs of near duplicates in time proportional to output plus something near linear. So linear is like unavoidable because, okay, we need just to read the data. And something proportional to output is also unavoidable. We just need to report the things. So it seems like the fastest we can hope for, especially assuming D is constant. And this is deterministic. So all previous approaches to like identifying similar objects were like hashing. And the hashing is inherently like randomized. So you're trying to compute fingerprints. If fingerprints coincide, then you check the real things. And here's a completely different thing. So there was no like no mapping. It's again based that the first thing we do, we build combinatorial nets, build this data structure. And then within this data structure, for every point, we look around. We can like from bottom to top, we can build the most similar points until we cross the threshold, and then we can stop. So basically, getting all near duplicates and stop. So we do not do any additional work. Just report near duplicates.
Do you know anything about the degree on this?
It's something like 4 or 5, maybe. Okay, so it's 7 for this part because it's combinatorial nets, and it's like 4 or 5 for this part. It is in the paper. I just don't remember. Yeah. Okay. So we also tried to address other problems like clustering. It's not very impressive, just to show you that you can address any old problems within the new approach. So there are many problems algorithmic problems that starting something like given endpoints in some metric space, do something. For example, identify k clusters such that the sum of intercluster distances is minimized. That's one form of cluster. You can do exactly the same. You can formulate any problems like this in combinatorial case. So you can say, OK, we are going to minimize rank functions. So minimize the ranks within the cluster. So good clustering is like when all internal ranks are small. And well, you should, again, build the combinatorial nets. And then it helps you to get a clustering which is approximately optimal up to this, unfortunately, very big factor. So it would be, but OK, the factor is big. But the good thing is that it's optimal not with respect to best clustering to this particular data set. It is that close to optimal clustering to any data set. Because the minimum value, since it is about integers, and for ranks we always have like 1, 2, 3, up to n, the minimal value for k clustering is like, there is a global minimum. So when we compare the quality of this approximate solution, we compare it to global minimum, not to minimum to a particular data set. OK, so that's just maybe not that interesting. But this result is really interesting. So if you know Voronoi diagrams, so they have one very, very wonderful property. If you draw a Voronoi diagram, and assuming you have some query point Q in mind, which probably do not belong to this Voronoi diagram. So there are like base stations of I don't know, T-Mobile or AT&T wireless network, and you are going to, and this is the person, and so we are going to find the nearest base station, and we are going to do it like by local search. So we're starting from this base station, and then we think, OK, probably this is not the optimal one. So we're trying to look around. We look at these adjacent Voronoi regions, and look, can we go closer to the person? So we go, say, which out of these three is most close? Probably this one. So we move here, and then we look here again, the neighbors. So we check this, this, and this, and see that this is closer. And then we check nearest neighbors for the adjacent Voronoi cells for this. So this, this, and this. All three are farther away than this particular thing. So we stop. We say, this is nearest neighbor. And this is always works. So once you are in some point such that all adjacent Voronoi cells are farther away than the current one is global, not just local. It's global nearest neighbor for the query point. So if some particular thing is better than all its neighbors, then it's better globally. It's like 2 lines proof. And here we can, so you can associate the graph with Voronoi diagram, like adjacency graph, which is called Delaunay graph or Delaunay triangulation. And so it has this property that the greedy walk over Delaunay graph will lead you to a nearest neighbor. But there are 2 problems. The out degrees might be very large. It might be region that is connected to all the others. And the length of the walk can be long. So you can walk long, long, long until you find. We found a way that, again, building combinatorial nets, you can build another graph, which we call visibility graph, that has just magical properties. So it has, OK, so the same construction time, subquadratic construction time. And then it has limited out degrees. So assuming d is constant, just logarithmic degrees. And that such that greedy routing deterministically always reach exact nearest neighbor in at most log n steps. So we solved both problems for Delaunay graph, small out degrees and fast convergence to a nearest neighbor. And this is kind of never seen before. OK, so just illustration for greedy walk. So you are in some point in visibility graph. This is visibility neighbors. You need to go to Q. So you go rightmost thing because it's the closest. Then you have another choice in this graph, visibility graph. So you go down, then you go down again. And then probably you don't have any good move. Better to Q, so report the point. OK, now I probably have 5 minutes for one technical trick I would like to show on the whiteboard. So this is related to constructing combinatorial nets, because combinatorial nets is the most useful thing. And even within the algorithm for combinatorial nets, it was reused in many contexts many times. And I think it can be used in some practical algorithms. Actually, I have never seen this trick in other nearest neighbors papers. Maybe it appears in some other algorithmic areas. I don't know. So assuming you build your combinatorial net for several levels. So you build a big ball of radius n, ball of radius n², and so on, up to some level 2r. So you cover all your data sets by combinatorial balls of radius 2r. And now you're going by greedy way to OK, so you probably copy these points, right, to the next layer. So you have twice smaller balls around them. But now they don't cover everything. So you need to cover many things. So OK, this is the point. And we are going to OK, so what's the greedy algorithm? We need just to write the ball around it and remove it and continue covering. The question is how to identify this small ball. We don't have ranks, so we do not have lookups. So what we do, we go up, then we go all neighbors, then we go down, and then we sort and keep just the r best. So that's the way. So when I'm standing and I'm trying to understand what is my, say, count people who are living in my county, if I don't know the county very well, so what I do, I go to the state, I look for surrounding states, like my state, adjacent states, then I go down to all people who are living there and sort them according to similarity to myself and keep just the limited number of the closest neighbors and say this is my county. What's the problem? The problem is that we use these links, right? So to build a new layer of net, we need these cousin links or these adjacent links. And now when we build it, say, assume we build the new layer, we have to fulfill our promises. So we need again to build the cousin links. And here the magic comes in. And this is probably a beautiful thing. So now we need to build a cousin here. So what we do again the same trick. We do again this up and down. So but now we don't go to, because we need a larger distance here, we go several layers up. So like on state level. Then again go. So depending on distance we need to find, we just identify the reasonable jump up. And then here we have cousin links. So we have all these cousin links. We check them. We go down, sort, and keep the best ones. And in this routine, we really extensively use the disorder inequality assumption, because the disorder inequality assumption, it works other way around. So assuming 2 points are really close in ranking, so they have something small here. Then if they are covered by some, say, 2r balls on the next level, by disorder inequality, by this rank inequality, this rank is relatively small. So these things really would be cousins to each other. So if you need to find this, we go this, we check all cousins, we go down, and then sort and keep real ones. OK, so coming to the conclusion, directions for further research. So first overview is about combinatorial framework. So we can study other problems that we're starting in the problem statements, like given endpoints, metric space, do something. Like given 2 collections of points, find the representatives of red points and blue points that are closest pair. We can try to solve this in combinatorial framework, or trying to identify the communities of much closer to each other than usually they are. Some cluster, bubble cluster, whatever. or some linear. So low distortion embeddings, we can also revise this topic, because now we can speak about the embeddings that have distortion on metric. We can look about ranking distortion. So how particular embedding change the ordering of points with respect to each other. And that's probably more meaningful than distances. Okay, next question is about exceptions. And this is really important. And also implementation and dynamic aspects. I actually believe that there would not be any big problems with dynamic aspects like insertion, deletions, and this changing metric. I actually never seen the old approaches to be revised in this sense. So when somebody writes down something about dynamic themes, they write either about deletions, insertions, or sometimes about moving objects. So similarity search in context of computer vision and the tracking the object. Sometimes they need this to, I don't know, avoid the crashes or something like this to track the nearest neighbors. But in the context of web, sometimes the metric is changing. So this relevance score for websites and queries, or for ads and websites, it's changing because you reevaluate factors, or you're getting more historical information, or whatever, or there are new hyperlinks. So it's changing every day. You don't want to rebuild your data set, the data structure. So that's the good question to think about. Yeah, and another thing is, the question is, how can we, out of the basic similarity measure, get in maybe a better measure? So what we did here, right, we forget about the real similarity values and start looking for ranks. This is one particular thing that we can call metric regularization. Maybe there are some other ways to do this, probably better ones. Well, there are some other things I'm interested to do in future which are not that related to similarity search. So similarity search in all my talk was about speed. So making algorithms faster, having less space. But you remember at the beginning of the talk I said that there are different performance measures. So what about like quality, or what about revenue or user satisfaction? And making like, what if you don't know exactly what is the relevance, and you need to find the most relevant thing, maybe not faster but just more relevant results, then I'm really interested to use human computation, so sometimes called artificial intelligence. So not machine learning, but people instead of machine learning. So like trying to plug in some places of algorithms, like people instead of. I have one example. So there is a thing which was developed in Microsoft Research, which is latent semantic analysis. So in context of recommendations, it's something like you have movies, and then you have latent factors. It's like new coordinates, and every movie is like has coordinates against these latent factors. And if there is a user and he has some interests, so we're trying to figure out his interests also in terms of these latent factors, and then find the most relevant movie. So, and the interesting thing that this first part, like identifying these latent factors, is done by computers. So it's like kind of matrix computation. The question is whether we can plug in like society, like computer users, to do exactly the same trick. And actually, if you look for example, the radios, this is another form of latent factor. So every radio station is a kind of latent factor. So there are editors who manually choose a subset here, and then you just choose which radio. And if you look for Last FM radio, they have tag radio. So you can just simply type in tag, and you will get the random sequence of music that was tagged with this tag. So, and this is like using social intelligence for solving the same problem, sometimes similarity problems. And I'm very interested in that. And there is another project which is, I'm right now just starting at Caltech, which is devoted to advertisements. And this is like trying to build something like Facebook, but for businesses. So this is a very applied project. Like build a bipartite social network between all businesses, all people, and make them communicate with each other. So I need another talk for this. It's a very big thing. Actually, I gave a talk yesterday at Ad Labs about this. But this is just at the beginning. And this project has also algorithmic problems. Probably the most funny one is I'm bored algorithm. So it's search without query, sometimes called queryless or query-free search. Just press the button and get some results. And to do it good. So welcome to my web page, to the page about nearest neighbors. And thanks to all my co-authors who contributed a lot to all this nearest neighbor things. So I have not covered this theme, which was a different approach to nearest neighbors about, instead of using combinatorial assumption, using some probabilistic assumption. But these two are like represent what I talked today about. So today I presented new framework, new algorithms, and some directions for further work. Thank you very much.
So one question for me. So on a future work slide, you had the sort of experiments and implementation at the end.
Uh-huh.
And it seems to me that's the key thing here. When you put the tag cloud up earlier and all these methods, sort of the garbage trail of history of all these methods people have tried and indexing methods to try to speed up nearest neighbor. The reason there's so many is because most of them actually don't work in practice. And so I'm curious, for example, even if you're ordered these to the fourth, it doesn't mean that the constant sounds super big in the implementation. So do you have any prognosis on what are you concerned about when you implement this and try it out? How well do you think it's going to work? What are the things that concern you in terms of whether it's actually going to? For example, I'll throw it on the gauntlet and say, do you really believe it's necessarily going to be faster than linear scan? Very fast, cache efficient linear scanning, which I'll tell you right now, 80% of the clever methods out there are not for reasonably high dimensional data.
To be honest, I don't have that good practical intuition. But I really believe it can be faster than linear scan. And an informal hand-waving proof is like clusterability hypothesis. So assuming the data set have some kind of clusterability, so it has some groups that lie close to each other and far from the remaining things. So if you look for like society, like people, websites, you can identify some kind of community structure. You can identify some groups. And the intuition behind any similarity search algorithm is to skip at once irrelevant communities. And I believe that this way or that way, it can be implemented to improve. So it doesn't mean that we can do all the clever things around linear scan for the remaining part, but we probably can save some work if we, on the preprocessing time, identify some community structure, and at search time, we quickly identify some irrelevant parts.
And the second question is, even if you manage to make that work, is it actually finding nearest neighbor in the original metric? For example, if you had a metric and you're using ranking to capture that,
Yeah.
say in the case of your Reuters and you're using cosine similarity and you're using that to rank the data, this closeness, then the question becomes, do you actually preserve the same, if you're going to use nearest neighbor as a classifier, for example, are you going to actually preserve the same complications when you use this ranking as you would if you had done the explicit nearest neighbor?
Yes.
Preserve the properties of what you're trying to achieve.
Yes, because I have not modified the problem. In the previous one, I was searching for, say, 10 nearest neighbors for nearest neighbor classifier. Here I can say I'm looking for points that have rank 1, 2, so on 10. I can find them, and the algorithm guarantees, if the model is true, to find exactly this
You're
one.
only preserving rank, right? Rank closeness. But your original metric was cosine similarity, right? And you induced the ranking.
So you mean the weighted nearest neighbor classifier when you weight the 10, say, nearest neighbor?
K nearest neighbor. But my main point is simply if you have a problem that does have a metric,
Uh-huh.
right? The same thing happens in these other things like
Yeah.
vantage point and
Uh-huh.
metric things. You may have an Euclidean distance and you turn that into a metric. You throw away your vector and you just have distances. The question becomes, are you actually preserving properties in the original space that you induced this? Because your representation is ranking that you're dealing with.
Yeah.
But the original problem might have been a Euclidean distance
Okay.
vector, dagger words, cosine similarities.
Okay.
And I'm just wondering, does your method actually necessarily preserve the original, distances in the original original metric space that you had, where you're only preserving, only proving, guaranteeing it's going to give you the nearest neighbor with respect to the rankings that you have.
But okay.
So it's not necessarily the same thing. Rankings are ordinal. They're not weighted by how far away they are. Right?
Yes, that's true. But I mean, the oracle is powered by actual distances. So as far as the oracle is powered by the original distances, I will get.
Well, we can talk about that.
Yeah.
Feel confident on that one.
Yeah. I feel confident, so that it would be the same. Yeah.
I actually have more of a comment than
Uh-huh.
a question, but you mentioned one of the areas of your further research
Uh-huh.
to look at the other metrics like the click-through rate or
Uh-huh.
revenue. And my recommendation would be to actually look at hybrid approaches, because in most domains, whether that's search or advertising or any of the other domains, you want to do really fast pruning where your current approach works really well, and then once you do the pruning of the majority of data points, that's when you start caring about the actual distance measure, and when you have the 10 points, you start caring, well, are 5 of them really close, and then the 6 and more are much further. So I think if you do the pruning and then you use other approaches for fine-tuning the very final result, I think that one might be very interesting and useful.
Yeah, thank you very much. I'm actually looking forward to combine this idea with other ideas. I'm not saying that other ideas doesn't work. It was just putting new assumption, but then under this assumption we can plug in any ideas. And at any point we can remember back that we have distances or we have coordinates, and then use hybrid algorithms that sometimes use just combinatorial form, and sometimes when it is appropriate use more information that we have. There is no particular reason to really forget forever this information.
One other question I'd ask is the typical other thing people do when they say that you come in on some number, like in your case D, is have you actually plotted out how D scales with N for data sets? So sometimes there's a dependency on N in practice, even though, so as your data set gets bigger, intrinsically it's more complicated and your D starts growing. So it could become
Okay, we really ran a series of experiments, and in all of them there was first thing that in worst case D was like N. So the third rank was like the order of rank by the first two are like 10. So 10, 10, and the 10,000, third one. But surprisingly, the average value does not scale with N, so it remains like 3 or 4 or 2. So whatever sample we take, it's like still like usually the third rank is pretty small one. I think one potential the explanation is like out of these 3 ranks, if you just simply take not the highest rank out of these 3, the ratio would be less than 1, right? So with fairly big chance it would be just smaller than 1. So that's why the average is really very small. But again, it's another good direction to more closely look and run more experiments.